I would now like to get into some specifically health-related kinds of uses of conversion factors using clinical data you might encounter in a hospital or a doctor's practice. So we see conversion factors coming up quite a bit when we need to, for example, relate the amount of medication to be given to a patient to that patient's weight. And so we can use that information and construct conversion factors from it. Here's another type of dosing information we might use. So it might say for every 10.0 milliliter dose, it contains 0.250 grams of vitamin C. Now we can make those into conversion factors. We can say every 10 milliliter dose has 0.250 grams of vitamin C, and this would be good for converting the grams of vitamin C to volume of doses, or we could write its reciprocal if we wanted to go from volume of dose to grams of vitamin C. Okay, let's go ahead and apply those clinical conversion factors to a pair of problems. So first, let's say that we have a case where a patient was given a 22.5 milliliter dose of the medication, and we want to know how many grams they would be taking of vitamin C. So their dose was 22.5 milliliters. That's your given information. They took in a 22.5 milliliter dose. We want to find out how much vitamin C they're taking in, so we need to cancel out the milliliters of dosing, and we want to convert that to grams of vitamin C. So which conversion factor do we want? Well, we want this one right here because it's got the milliliters in the denominator. So we have here 10.0 milliliters of dose would give you 0.250 grams of vitamin C. And so again, we notice here our important pattern, the diagonal pattern, in terms of what values will cancel with each other. And let's go ahead and put this in the calculator. So I enter this in as 22.5. We multiply by everything in the numerator, so times 0.250, and then divide by 10. Divide by everything in the denominator. And my calculator gives me 0.5625. So the calculator answer here is 0.5625. And that would be in grams. Now we have to worry about significant digits here. We weren't told that any of these numbers here were exact. So if we look at this, there's 3 significant digits, 3 significant digits, 3 significant digits. So it would make sense that our final answer here should have 3 significant digits. So that would be 0.56. There's my first 2. And then the 2 is rounded up because of the 5 being next door. So when they took that 22.5 milliliters, they got 0.563 grams of vitamin C. Let's try a similar problem. How many milliliters would they need to receive 1.15 grams of vitamin C? Well, so we're going to say 1.15 grams of vitamin C is our given. That is a 5. And now we're going to use the other conversion factor. So we're going to say there's 0.250 grams of vitamin C in a 10 milliliter dose. And I don't really need to write dose there. And I double check vitamin C grams. See, they're diagonal to each other, so they cancel. So if we put this in the calculator, you have 1.15 times 10 divided by 0.25. And that comes out to, the calculator is saying 46. But that wouldn't be the correct number of significant digits. This has 3, 3, 3. So remember, when you get less significant digits from your calculator, you just need to add on zeros in the correct way. So if this is 46, that's in the ones place. We're going to need a 0 in the tens place. And the unit that's left over is milliliters. Oops. Milliliters. So 46.0 milliliters is how much they'd have to be given. Next, we take a look at measuring temperature. Temperature is a measurement of average kinetic energy of a body. And when we say kinetic energy, what we're specifically referring to is the motion of the particles that are in whatever it is whose temperature we're measuring. So let's compare, for example, hot water and cold water. Hot water is obviously at a higher temperature than colder water. That means there's going to be more motion associated with the water molecules in the hot water. They're going to be moving around on average much faster than the molecules in the lower temperature, colder water. Temperature is not the same thing as heat. Heat is measured in units of energy. There is definitely a relationship between temperature and energy, but they are not exactly the same thing. So we have 3 different units that we commonly use for temperature. So up until now, you've probably used Fahrenheit degrees more than anything else. And that's usually how we measure our temperatures and weather in the United States. But it's not very practical for scientific use. Celsius is much more practical. It's based on the boiling point and the freezing point of water, as we're going to see. Kelvin initially seems a little bit intimidating. It is the SI unit of temperature. And Kelvin is very important because it allows us to define an absolute bottom temperature. So 0 Kelvin is called absolute zero. And we can't even get to 0 Kelvin. We can get extremely, extremely close using very sophisticated instrumentation. But we can't get to 0 Kelvin, and certainly we cannot get lower. So while Fahrenheit has negative temperatures and Celsius has negative temperatures, when we're measuring in Kelvin, we can get no negative temperatures. So let's compare the freezing and boiling points of water using these different scales. So I want to first start off by looking at Celsius. So Celsius, we see the freezing point of water is 0 degrees, and the boiling point of water is 100 degrees. That's not a coincidence. That was defined when Celsius was created. Next, look at Kelvin. What do these numbers have in common with Celsius? Well, you'll notice that if you go up 100 degrees Celsius, you're also going up by 100 Kelvin. So 273 to 373. So going up by 1 degree adds a degree in either scale. Fahrenheit, on the other hand, is quite a bit removed and different from these. Adding 1 degree Fahrenheit doesn't quite add a degree Celsius. And also these numbers aren't at all based on water. So what we do need to be able to do is convert between them, and so we'll look at some formulas for that in a moment. This is just a nice piece of artwork which shows you the difference between them. As I said a second ago, 0 degrees Celsius, 273.15 Kelvin are the same temperature. It takes 100 degrees in either of these temperatures to increase to the boiling point of water, whereas it takes 180 Fahrenheit degrees. And as I said a moment ago, Fahrenheit degrees are smaller than Kelvins or degrees Celsius. So if we want to convert between the different temperature units, what we do is we use these formulas here. Now all of these involve addition or subtraction, and therefore we can't just simply multiply by conversion factors. Is it necessary to memorize these? Well, not at this point. But it is important to understand how they're written. So whenever you see TC, that just means you substitute in the Celsius temperature. So this would allow us to go from Celsius into Fahrenheit. We just take the result of this calculation to find that. Okay, so let's go ahead and carry out these conversions here. We have body temperature as 98.6 degrees Fahrenheit. So that's just TF. And we want to convert that to Celsius and Kelvin. So first of all, let's go ahead and convert this to Celsius. So I can use this formula right here to do that. So temperature in Celsius is going to equal temperature in Fahrenheit, which is 98.6 minus 32 over 1.8. So we've got a mix here of addition, subtraction, and multiplication, division. So for SIGDIC purposes, I'm going to split this up. So the first part would be in the numerator. That would be 66.6. The 32 we're going to treat as an exact number. And then we need to divide that by 1.8, which also turns out to be an exact number. And when we're done with that, we should come out with 37.0 degrees Celsius. And again, that's because the numerator has 3 significant digits, and we said this was an exact number. So 37.0 degrees Celsius. I'd like to now convert that into Kelvin. So to convert that into Kelvin, I'm going to use the formula right there. So temperature in Kelvin. Notice we don't actually use a degree sign for Kelvin here. So temperature in Kelvin is simply the temperature in Celsius plus 273. And when we do that, we're going to come out with 310. And treating that as exact, I'll put that as a 0.0. And the units would be Kelvin. Technically, if I wanted to go further, I should have added 273.15. So 310.15 or 310.2 Kelvin would have been a better answer in terms of accuracy. But this is going to be good enough for what we need to do here. And the last couple topics we're going to approach in this chapter include density and the very closely related specific gravity. So we define density as a ratio, just like many things so far in this chapter have been. It's a ratio of mass to volume of any particular substance we're looking at. So as a formula, we can write it like this: density equals mass, usually in grams, over volume, and we're usually going to do that in milliliters or cc, which is cubic centimeters. So if we want to find the density of anything, all we need to do is find our object that we want to go ahead and get the density for and weigh it to get its mass, and then measure its volume and divide one by the other. Now you can use any amount of this. This is what we call an intensive property. It doesn't matter how much of it you have. If you had measured the mass and volume of a particular substance and found the density, then let's say you went and got something else. Let's say you got twice as much of that substance. Its mass would be twice as much. Its volume would also be twice as much. So 2 times, the 2 cancels out. So it's ultimately a ratio that stays constant, regardless of how much you use. It can change, however, with temperature, but we're not going to worry too much about that. So let's solve a problem involving density. So let's say we have a block of metal and its mass is 68.5 grams and its volume is 14.3 centimeters cubed. And we'd like to find its density. Okay, so let's go ahead and solve for that. It's actually quite simple. The mass is 68.5, so let's write down here density equals mass over volume. So the mass is 68.5 grams, and the volume is 14.3 cubic centimeters. And that's usually the unit for volume we use for solids. So we just go ahead and figure this out. So 68.5 divided by 14.3 is 4.79. Oops, let's rewrite that. 4.79 grams per milliliter for that metal. So if we were to write this in words, 4.79 grams of this metal occupies, and now we're going to see something very important, the word per. Per means for every one. So 4.79 grams for every 1 milliliter. Actually, we used centimeters cubed here. Let me change that. Centimeters cubed. This is one of those cases where the 1 is not treated for significant digits. The significant digits are all here. So there's 3 significant digits. Densities are not exact numbers, so if we used this, it would have to have 3 significant digits in it. And likewise, we could always read it the exact opposite way. Every 1 centimeter cubed of this metal has a mass of 4.79 grams. So if I had 100 centimeters cubed of the metal, what would its mass be? Well, if I multiply the volume by 100, I just have to multiply this by 100. It's a ratio. So its mass would be 479 grams. To find the volume of some objects with standard shapes, all we have to do is use a formula. So, for example, if we're trying to find the volume of a cylinder, we know that the volume of a cylinder is simply the area of its base, which is pi r squared, times its height. Or if it's a cube, it would be the length of a side cubed. But what if we're trying to find the density of something with a very odd shape? Well, so long as it doesn't dissolve in water or react with water, what we can do is we can take our object and immerse it in a known volume of water. Think about this. This is just like when we take a bath. When you take a bath, the water level as you sit into it rises up. By how much does it rise up? It rises up by the amount of your volume. You are said to be displacing water. And so that's essentially exactly what we're going to be doing in this particular case. If you can't use water, you could always use some other liquid that your substance doesn't react with, like oil or what have you. It doesn't really matter, so long as you have a liquid. So the way that we find the volume then is we look at the volume after you have added your object. That is the volume of the object plus the water. And then you subtract the volume of the water, which you had written down before you put the object in. And this is called volume by difference. So let's apply that in a problem. Okay, so what we have here is a practical application of measuring volume by difference. So let's read this problem. To measure the density of zinc, a chemist drops a cylinder of zinc weighing 98.4 grams into a graduated cylinder that has 15 milliliters of water. The volume in the cylinder reads 28.8 milliliters after the zinc settles to the bottom. What is the density of zinc? Well, to find the density, what do we need? We need the mass, which we already have here. So here's the mass, and we need the volume. And the volume is neither of these numbers. This number is zinc plus water, and this is just water. So what we need to do is we need to find the volume by subtracting. So we have 28.8 milliliters is the volume of the zinc plus water. And we want to subtract 15.0 milliliters. In other words, we're subtracting out the water here. And that leaves us with just zinc. It's very important that you not include anything else in a density. It has to be only whatever it is that you're trying to determine the density for. So if we subtract here 28.8 minus 15.0, this would be 13.8 milliliters. And since this is a solid, we usually write that in centimeters cubed instead, which is the same number. Now to find the density, it's the mass over the volume. So the mass we already found here. It's 98.4 grams. Sorry, those look like zombie numbers. Let's take a look at those again. Yuck. Yuck. So here we go. 98.4 grams. Much nicer. And the volume is 13.8 centimeters cubed. I have a conversion here, but we always do the division. And so let's divide that. We have 98.4 divided by 13.8. And that comes out to 7.130. And with 3 significant digits, that would be 7.13. And the unit is grams per centimeters cubed. They're different types of units, so they can't cancel out. Now that we have that, let's apply that in a couple different problems here. So you see, I can take the density and rewrite it as conversion factors. Remember, I said this is per 1 ml or per 1 centimeter cubed. I'll leave it as milliliters here after all. So let's go ahead and use the information in a practical way. So let's find the volume of a 425 gram piece of zinc. Well, it doesn't matter how much we have, this ratio still holds. So how do I want to use this? Do I want the conversion on the left or the conversion on the right? I'm going to want the conversion on the right because that will cancel out the grams. So the volume here would be, well, we start off with 425 grams of zinc. That's the symbol for zinc, by the way. And there are 7.13 grams of zinc for every 1 milliliter. And we already said that a milliliter is the same as a centimeter cubed. So let me just go ahead and change that back to centimeter cubed. And that saves us a step later. So doing this division, 425 divided by 7.13 is 59.607. We need 3 significant digits, so that would be 59.6. Make sure that your units make sense. We got rid of grams. The unit we wanted was centimeter cubed, and that's what we have here. So 59.6 centimeter cubed, or we could say 59.6 centimeter cubed of zinc. What is the mass of a piece of zinc with volume? Now, the difference between these two problems is the top problem, I gave you the mass and I asked you for the volume. Here I'm giving you the volume and asking you for the mass. So we just use the other conversion factor. So I have 100.0 centimeters cubed. As we said, we can change milliliters to centimeters cubed. They're the same thing. So for every 1 centimeter cubed, that is 7.13 grams. And we're only talking about zinc here. So that's an easy enough one to do in our heads. I gave you 4 significant digits here, but the density we only know to 3. So we have to round to 3 significant digits. So this would be 713 grams. So the last topic I'm going to cover in Chapter 1 is specific gravity, which is closely related to the density. The definition is going to sound a bit confusing. The formal definition says that specific gravity is the density of whatever it is what we're measuring divided by the density of water at 4.0 degrees Celsius, which is water at its maximum density. Now that seems rather difficult and convoluted until we see that the density of water at that temperature is 1.000. And you're going, well, okay, if you're dividing by 1, you're not changing anything. Not quite true. You're dividing by 1.000 grams per milliliter. So when you divide density by this, the units cancel, and so that simply leaves us the exact same value as the density, but with no units. That's all we do. We essentially strip the units from the value. So if we want to know the specific gravity of a saline, that's a saltwater solution, with density 1.02 grams over milliliters, it is simply going to be 1.02 with no units. So 1.02 grams over milliliters divided by 1.000 grams per milliliters. And these cancel out. The way you could look at this is you're dividing one fraction by another. So this would be 1.02 grams over milliliters. And remember, to divide by a fraction, it's the same as multiplying by its reciprocal. So the units completely cancel. And it's just 1.0. No need to show the work on this. If you had just said 1.02, that would have been fine. This ends our video lectures for Chapter 1. Thank you for watching.